Okay, students, let's continue with section 2.6. Okay, inverse of a square matrix. Okay, 2.6 is the inverse of a square matrix. Okay, okay, definition. If matrix A and matrix A to the -1 power, which we're called the inverse, okay, are n by n matrices, so they're square matrices, such that if A multiplied by A inverse equals IN, okay, the identity matrix. If I multiply the two, I get the identity matrix. And that is also commutative. A inverse times A is equal to the identity matrix. Then we denote AI, or sorry, A to the -1 power as the inverse of A. When A inverse exists, we say that A is invertible. When A is not invertible, okay, when A is not invertible, we say it is singular. It doesn't have a partner. It is singular. Okay, not all matrices have an inverse. Okay, not all square matrices have an inverse. Okay, let's find a inverse, and we're going to use Gauss-Jordan elimination to help us find the inverse of A inverse. Okay, let A equal 1, -1, 2, 2, -3, 3, 1, -1, 1. Okay, use the Gauss-Jordan method. Find A1, or sorry, A inverse. Okay, so the goal here is to take A and match it with IN in an augmented matrix, and then transform that augmented matrix into IN A inverse. Okay, by turning A into the identity matrix, it will turn the identity matrix into A inverse. Okay, so we're going to use an augmented matrix with A, 1, -1, 2, 2, -3, 3, 1, -1, 1, augmented matrix with the identity matrix for N. This is a 3 by 3, so this is going to be I3. So this was matrix A. This is I3, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And now what I want to do is I want to treat this all as one matrix, but end up swapping the identity matrix I3, get it over here. And what that will do is if I can get the identity matrix I3 over here, then I will have the inverse, A inverse over there. Okay. So use row operations to swap the identity matrix. To swap I3. Okay, and we could do this with any size square matrix. It could be I3, I4, I5, IN. Okay, so let's think about what we want our first operation to be. We already have a 1 here, which is nice. Okay, I'd like to get a 0 here. Okay, and so let's multiply row 1 by -2 and add it to row 2. Okay, so let's try that. A1, 2, -2. Okay. So if I multiply by -2, I get -2. I've got 2. We've got -4, -2, 0, 0. Okay, and let's add that to row 2, replacing row 2. Okay. So we're going to get row 1 stays the same. 1, -1, 2, 1, 0, 0. Okay. And then 0, 2 and -3 is -1. 4 and -3 is -1. Okay, -2 and 0 is -2. 0 and 1 is 1. And 0 and 0 is 0. Okay. And then row 3 stays the same. 1, -1, 1, 0, 0, 1. Okay. So next step in the augmented matrix. Okay, now let's see what we want to do. I want to get rid of this 1 here. Okay, let's try to get rid of that 1. Okay, and so I'm going to get multiply -1 by row 1, add it to row 3. So A13, -1. Okay. So and then we'll replace row 3 with it. So I'm just going to negate the top row. -1, 1, -2, -1, 0, 0. Okay, now add that to row 3 and replace row 3. So the first 2 rows don't get replaced or affected. 1, -1, 2, 1, 0, 0, 0, -1, -1, -2, 1, 0. The third row becomes 0, 0. Well, that's kind of nice. -2 and 1 is -1. And then, let's see, what, -1, 0, and 1. Okay. So the next step. Okay, the next step is I would like to, I'd like to get this guy to be a 0. Okay, we're going for Gauss-Jordan elimination. And so we want this to not only be a lower triangular matrix here, okay, we want it to be an upper triangular matrix as well. So I want to get that identity there so that this upper triangle is also zeros, and I just want ones along the diagonal. Okay, so let's go back. Okay, that's fine. So there we go. Okay, so yeah, that original -1, that's what I want to get rid of. So how can I get rid of that -1 without affecting anything else? Well, I'm just going to multiply row 2 by a -1 and add it to row 1, and that will help eliminate that -1 in row 1. So that's going to be a 2, 1, -1. Okay, and so row 2 is going to be negated. So that's going to become a 1, 1, 2, -1, 0. And I'm going to add that to row 2, or row 1, excuse me. Okay, so row 1 now becomes 1, 0. That's what I want. I want that 0 there. 2 and 1 is 3. 2 and 1 is, again, 3. -1 and 0 is -1. And 0. Okay, so that's my first row. Okay, and then the second row remains unaffected. -1, -1, -2, 1, 0, and then the third row 0, 0, -1, -1, 0, 1. Okay. Okay. So again, what's the goal? The goal here is to get zeros everywhere on this side. I want to get zeros everywhere and ones along the diagonal. Okay. Okay. Okay, let's do let's multiply. I'm just gonna multiply the second row by -1, and that's gonna lock in that 1. Okay, that's gonna change this -1 to a +1. If I multiply the second row through by -1, multiply row 2 by -1, I will get 1, 0, 3, 3, -1, 0, 0, 1, 1, 2, -1, 0. Okay, and then 0, 0, -1, -1, 0, and 1. Okay. Okay, so now what I want to do is I'd like to get rid of, I've got basically my first two columns set. I need to work on the third column now. Okay, I need to get this 3 to be a 0. And I want to get that 3 to be a 0 without affecting the 1 and the 0 that I worked so hard to achieve. Okay, I want to get this 3. So what can I do to get that 3 to be a 0? Well, if I multiply this first row through by 1, no, if I multiply the third row through by 3 and then add it to row 1 and then replace row 1, that +3 should cancel out because I would end up with a -3. -3 there. If I multiply 3 by 3 on row 3, I'll get a -3 and a +3 and a negative and a negative. No, I'll get a -3 and -3, a 0 and a +3. Okay, the others are zeros. Okay. And so, yeah, let's do that. So this is going to be A31 of just 3, multiply 3 by 3. And then we're going to add those together, replacing row 1. Okay, so my resultant vector, okay, is going to be 1, 0, 0. Okay, 0. Well, that's kind of interesting. Okay, 1 and -1 and 0 is -1. And 0 and 3 is 3. Okay. And then the other two rows are unaffected. -1, and then 2, -1, 0, and -1, 0, 1. Okay, okay, next step is I would like to get rid of this 1. Okay, I want to make that a 0. So let's work on that one. And what can I do? I can just add rows 2 and 3 together. Okay, the way that I would designate that is I would say that I'm going to take row 3, multiply by 1, and add it to row 2. Okay. Okay, and so multiplying by 1 doesn't affect the row at all, row 3, and then I'm going to add it to row 2. And so that's going to get me 1, 0, 0, 0, -1, 3. Okay, 0, 1, 0. Okay, adding those two together, replacing row 2. This is going to be a 1. That's going to be a -1 and a +1. Okay, and then the last row is going to be 0, 0. Okay, -1, -1, 0, and 1. Okay, and we're one step away from getting our inverse. Okay, because this is almost I3. It is practically there, except for the fact that I have a -1 here, and I'd like that to be a +1. So I'm just going to multiply the third row through, multiply the third row through by a -1, and that should do it. Okay, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, and then we have 0, -1, 3, 1, -1, 1, and then that's going to be 1, 0, -1, 1, 0, -1. Okay, and what this gives me is this gives me I3 on one side, okay, on the left side, which is what we wanted, and it gives me A inverse on the right side. So my A inverse would be equal to 0, -1, 3, 1, -1, 1, and 1, 0, -1. And that is A inverse. Okay, and we can check this by multiplying A and A inverse together and see if we in fact do get the identity. So what was A again? Okay, A was 1, -1, 2, 2, -3, 3, and 1, -1, 1. Okay, that's what A was. So if we take A times A inverse, we would get 1, -1, 2, 2, -3, 3, 1, -1, 1 times 0, -1, 3, 1, -1, 1, and 1, 0, -1. Okay, so now let's do row and column, summing up as we go. So first row, first column. Okay, what is that going to become? Let's do a big 3 by 3 matrix here. Oops. Okay, give myself plenty of room to check this. So this is going to become 1 times 0 plus -1 times 1 plus 2 times 1. Okay, that will give me my first row, first column entry. Okay, I'll end up with 9 entries. Okay, total. Okay, let's do first row, second column. First row, second column, that's going to give me 1 times -1, 1 times -1, plus -1 times -1, plus 2 times 0. Okay, and then let's go for the first row, third column. So that's 1 times 3 plus -1 times 1 plus 2 times -1. Okay, so now let's move on to the second row. Okay, let's move on to the second row. So we're going to do second row, first column. Okay, so that's going to become 2 times 0 plus -3 times 1 plus 3 times 1. Okay, and then we'll just keep going. I think I'm not going to highlight. I'll just keep, well, maybe I will. I can make the highlights big, then I can erase them easy. So 2 times -1, okay, is 2 times -1 plus -3 times -1 plus 3 times 0. Okay, and then the next one is 3. 2 times 3 plus -3 times 1 plus 3 times -1. Okay, okay, last row. Oof. Okay, last row is this guy here. Okay, times the first column. That's going to be 1 times 0. Okay, that's going to be 1 times 0 plus -1 times 1 plus 1 times 1. Okay, and then we have 1 times -1, next column, over 1 times -1 plus -1 times -1 plus 1 times 0. Okay, and then last row, last column, third row, third column. Okay, 1 times 3 plus -1 times 1 plus 1 times -1. Okay, and if this is the inverse, some nice things should be happening. Okay, when I add these together. For the first entry, we've got 1 times 0, which is 0, plus -1 times 1, which is -1, plus 2. So I've got 0, -1, and 2. That all adds up to 1. Okay, maybe I'll go down. 2 times 0 is 0. Okay, I'm going down, not over. Okay, 2 times 0 is 0, plus -3 times 1 is -3, plus 3 times 1, that's +3. So I've got 0, -3, and +3, that's a 0. 1 times 0, keep going down, 1 times 0 plus -1 times 1, that's -1, plus 1 times 1, that's +1, so 0 plus -1 plus 1, that's 0. Okay, next column. Second column, first entry, first row, second column. -1 1 times -1, that's -1. -1 times -1, that's 1. So I've got -1, 1, and then 2 times 0, that's 0. Okay, let's go down to the center. 2 times -1 is -2, plus -3 times -1, that's 3. So -2 plus 3 is 1, plus 3 times 0 is 1. Okay, down, 1 times -1 is -1, plus 1, because that's -1 times -1. So -1 plus 1 plus 0 is 0. Okay, third column. 1 times 3 is 3, plus -1 times 1 is -1, plus 2 times -2 is -2. So I've got 3, -1, and -2, which is 0. 2 times 3, which is 6, plus -3 times 1, which is -3, plus 3 times -1 is -3. So 6 minus 3 is 0. And 1 times 3 is 3, very last bottom corner, last entry. 1 times 3 is 3, plus -1 is -1, times 1 is -1, plus 1 times -1 is -1, so it's 3 minus 1 minus 1 is 1. And that does equal I3, so it does check. Pretty cool. Okay, so let's look at a theorem. Okay, if A inverse exists, then the system of equations A x is equal to B has the unique solution okay, it has the unique solution of x, my column n vector of variables, x, the variables is going to equal A inverse times the B vector, okay, the B column n vectors, n vector, okay, of constants. Okay. Okay, we'll get to this theorem in a second. Okay, I want to throw out well, let's go directly into problem 2 actually. We'll save the next theorem for after that. So let's see if we can solve a system of equations using the inverse. So solve the following system using A inverse. Okay, so I have x1 minus x2 plus 2x3 is equal to 5. 2x1 minus 3 x2 plus 3x3 is equal to 5. Okay. And then we have x1 minus x2 plus x3 is equal to 2. Okay. And so let's put this into the coefficient matrix times the variable matrix times the constant matrix. Okay. So what's the coefficient matrix going to look like? What's A going to look like? Well, lo and behold, it's 1, -1, 2, 2, -3, 3, and 1, -1, 1. And if I were to multiply this by the variable matrix x1, x2, x3, I would get back out my original system of equations here on the left side, because I would get, if I did matrix multiplication, I would do this times this times this, and that would give me my first row, first column entry. And so it'd be 1 times x1 is just x1. That's the x1 there. -1 times x2 is negative x2. And 2 times x3 is 2x3. And I could do that with each row. And it would come out as my system of equations. Okay, if I set them equal to my constant matrix, which is 5, 5, 2. Okay, so I've got my coefficient matrix A, I've got my variable vector B, and I've got my constant vector, my variable vector X, my constant vector B. Okay, and so they're saying that if I can find A inverse, then X, my X vector, is going to be x1, x2, x3 is equal to A inverse times my B vector, my B column 3 vector. Okay, 5, 5, 2. Okay, and so I just want to find my A inverse. Well, we already did all of the work for that. That was problem number 1. Okay, A inverse was calculated, or derived, I should say. We didn't really calculate it, we derived it in problem number 1. Okay, because we use a little forethought in how we want to produce the lesson. And so we let A here be equal to 1, -1, 2, 2, -3, 3, and 1, -1, 1. And that produced an inverse, A inverse of 0, -1, 3, 1, -1, 1, and 1, 0, -1. Okay, so this is a 3 by 3 matrix, and this is a 3 by 1 matrix, and so this should produce a 3 by 1 matrix. The columns in the first matrix and the rows in the second matrix match up, and so that would give me a resultant matrix of a 3 by 1, which is what my variable matrix is going to be equal to. Okay, so let's multiply this out. We're going to get x1, x2, x3 is equal to, 0 times 5 plus -1 times 5 plus 3 times 2. Okay, we're going to get 1 times 5 going to the next row. Okay, always multiplying by that first column because we're only going to have one column. Okay, 1 times 5 plus -1 times 5 again. Okay, and then 1 times 2. And then 1 times 5 plus 0 times 5 plus -1 times 2. Okay. And we get x1, x2, x3. Okay, then to be equal to 0 plus -5, well, that's going to be -5 plus 6. So 0 plus -5 plus 6. Okay, and that's going to equal 1. Okay, that equals 1. Okay, and then the next row, 1 times 5 is 5. That's a -5, so those are going to cancel, and then I'm just going to be left with 1 times 2, which is 2. So that's a 2. And then 1 times 5 is 5, plus 0 times 5 is 0, plus -2. So -1 times 2 is -2. And so that's a 3. So when we max this all up, we would say that x1, x2, x3 had to have been equal to 1, 2, 3. And so x1 would be equal to 1. X2 would be equal to 2, and x3 would be equal to 3. And so we've solved our system of equations. We can write it like that, or we could write it as a point. It really doesn't matter. Okay, either way is fine. Okay, so it has a unique solution. So if it's invertible, then we're going to get a unique solution, which is kind of nice. Okay, if it's not invertible, then we may not get a solution, or we might get an infinite number of solutions. Okay, let's go over 3 theorems real quick about inverses. Okay, so the theorem is let A be an n by n matrix Okay, let A be an n by n matrix. We say that A is invertible if, and only if, the rank of A is equal to n. So if we were to use Gauss-Jordan elimination on this, and it came out that the rank, after using Gauss-Jordan elimination, the rank is n, means that we have definite values in each of the 3 rows. Okay, no rows of zeros or anything messy like that. But if it ends up with an n by n matrix having rank n, then it is invertible. Okay, so that's the first theorem. Okay, second theorem is if A and B are invertible matrices, okay, then A inverse is invertible, and the inverse of the inverse is, we would get back to A. Okay, okay, B, the product AB is invertible. Okay, so if A and B are invertible, then the product is invertible. And, okay, AB inverse would be equal to B inverse times A inverse, and that's not commutative. Okay. Okay, and then C, AB inverse times AB would be equal to B inverse times A inverse A times B. Okay. And why is this? Well, this is true because a matrix and its inverse, when multiplied together, the AB matrix would be a new matrix based on the product of AB, but the inverse of the resultant AB matrix would just be I sub n, whatever the definitions of the dimensions of that would be. Well, let's see what happens over here. Over here, we're doing A inverse A first, so that's IN. And then I would get B and B inverse, right? Okay, but if I took this multiplication in order, B inverse times IN, what's anything times the identity matrix? Well, anything times the identity matrix is just itself. So if I did this B inverse IN, I would still get out B inverse. And then I would multiply by B, but what's B inverse times B? It's just the identity matrix back out again. And so that checks, okay? So these three statements do hold. Okay. And this will come in handy. C will come in handy when I have to kind of start chopping things down. Okay, we can say, oh, well, we have A, B. Well, we can just invert A and then invert B. Okay, and then we would end up with the identity matrix. Okay, last theorem for this section. Okay, if A inverse exists and the transpose is invertible, then A transpose inverse is equal to A inverse transpose. Okay, so that's kind of a nice little thing as well. If we take the inverse of the transpose, that's the transpose of the inverse. Okay, that's cool. Okay, and that'll do it for this section, 2.6, and I will see you in the next video.